The next problem that we'll talk about on the review is problem number 22, which involved figuring out the square root of 691 without the use of a calculator. To do this, the trick is to kind of group the digits by 2. So starting at the decimal point, these two digits will be together, and then the 6 will be together. And then we kind of play Price is Right. The perfect square that is closest to 6 without going over is 4. That's 2 squared. So I'll put a 2 here. And then 2 squared is 4. So subtracting, I get 291. The next thing that I do is take the number here and double it. And I need to put one number here so that 40-something times the something is as close to 291 as I can get without going over. Okay, so let's see what we get. So obviously, let's just do this by trial and error. 41 times 1, 42 times 2, 43 times 3, 45 times 5 is 225, getting close. 46 times 6 is 276. 47 times 7 is too big. So 46 times 6 looks like is the correct answer, 276. So let me put the 6 here and the 6 here for 276. So 26 point. Subtracting, I get 15 here. Then I bring down the next two zeros. Here, double the number that's here, 26. So 26 times 2 is 52. And then I do Price is Right again, 520 something. So 520 something times a something. I want that to be as close to 1,500 as I can without going over. Here, if I took 523 times 3, that's clearly too big. So 522 times 2 is 1044. So I need a 2 as my next digit. So 522. Multiplying, I get 1,044. And so subtracting, I get 456. So I get 26.2. Then I would bring down the next two digits and then continue. We know that there's going to be an infinite number of digits because it did not work out to be a perfect square. Now, why does this trick work? Well, first let's check that it actually did work. If I take 691 and take the square root of that, I do indeed get 26.2 something. Okay, now why does this work? The idea here is that when I found the 2 here, I knew that I'd have 20 something squared to be equal to 691. Okay, now let me square out the left-hand side. I get 400 plus 40 x plus x squared equals 691. Okay, now if I subtract the 400 over to the right-hand side, that gives me 291, which is the number that you see here, 691 minus 400. What's here remaining here, after I subtract the 400, would be these two terms, and I can factor an x out of that, which is 40 plus x times x. And this takes the place of what you see over here, 40 plus some number plus the next number. And x is going to be 6 point something or another. Then if I actually solve this with the quadratic equation, the idea is that here it's not going to be exactly equal, so let me get the integer x that is as close as possible to 291 without going over, which gives me the 6. Then continuing the logic, I would get the next decimal places using basically this base 10 argument for getting the next few places. So that's anyway the logic as to why that works. Okay, now for the final example, let's talk about problem number 25, which, if I can get the mouse to work here, involved finding the base 3 pattern was similar to the problem that was done on the homework. Now, for the homework, the trick was that on one card, you had digits where the first digit was all ones. Okay, so you had one card on the homework where you had all the ones digit was all equal to 1. So this would be like this. So written in base 2, the cards on the first card would have this pattern. The second card, the 2's digit was all ones. And so writing out all the possibilities, this would be the pattern for the digits on the second card. For the next card, the 4's digit had all a 1 in the 4 slot. And so starting off, this would be the pattern for the cards on the third card. Next one would go 1 1 0 0. Next one would be 1 1 0 1, and so on. So that was the pattern that we saw on the homework. The same idea can work in base 3, where I will take cards that have the same digit in either the 1's place or the 3's place. So writing out in base 3, I would have a card that would say, let's see, 1 in the first digit, or I could have 1 1, or I could have 2 1. Continuing on, I could have 1 0 1. I could have 1 1 1. I could have 1 2 1. Continuing in 2 0 1. 2 1 1. 2 2 1. And so for all these cards, I would have a 1 in the 1's digit. That would be the first card. The second card would be all 2's in the 1's digit. So 2, then I could have 12, 22. Then I have 1 0 2, 1 1 2, 1 2 2. Continuing, I'd have 2 0 1, 2 1 1, and 2. Sorry, they should all be 2's. Then 2 2 2. Okay, so that's the first digit. So now we do the same thing for the second digit, where I could have all 1's in the second digit. So that's the possibilities for small numbers. Then I go up to where I'm in the hundreds, which would be in base 3 the 9's digit. And then finally, where I'm in the 200s, or 2 times 9 or 8, or numbers that are at least 18. So these are the possibilities where I have all 1's in the second digit. And then same thing for the 2's, 2 0, 2 1, 2 2, 1 2 0, 1 2 1, 1 2 2. Then continuing, we get 2 2 0, 2 2 1, 2 2 2. Lastly, we do the same thing where I have 1 in the 9's digit, the third digit, and I list out all the possibilities for the other 2 digits that could happen, as long as the top first digit is a 1. And finally 1 2 2. Last card would have a 2 in the first digit, or the 9's digit, and then I list out all the possibilities for the remaining 2 digits. Almost done. 2 2 0, 2 2 1, and 2 2 2. So this would be the base 3 representation for the cards. Now that's the base 3 representation. Let's turn this to ordinary base 10 representation. So 1 in base 10 is 1. Here it's 1 times 3 plus 1, which makes 4. Then I have 2 times 3 plus 1, which makes 7. Then I have 9 plus 1 times 9 plus 1, which makes 10. And let me continue listing these out. 13, 16. Here on this one I get 19. Then 22, then 25. So that's the first card written ordinary base 10. For this pattern, it'll be 2, 5, 8. So this one is 2 times 3 plus 2, which makes 8. Then 11, 14, 17, 20, 23, and 26. So that's the first card. That's the second card. Whoops. So here's your second card. Next card, we have 3, 4, and 5. Here it's 9 plus 3 makes 12, then 13, then 14. Now it's 9 times 2 plus 3. So 9 times 2 is 18 plus 3 makes 21, 22, and the last one is 23. 2 times 9 plus 3 plus 2 should be 23. Okay, fourth card. So here I have 2 times 9 plus 0, so that's going to be 18. Or sorry, 2 times 3 plus 0 is 6, 7, 8. Then hits 9 plus 6 for 15, 16, 17. Then finally over here it's 2 times 9 for 18, plus 6 makes 24, 25, and 26. Alright, over here we have 9 continuing up to 17. If you actually check this, so let me just write those out quickly. All the numbers from 9 to 17. And for the last one, I'll need a little bit more space, so let me get rid of some stuff up here now that we've already got this. Let me clear this off. So for the very right column, I'll put that up here on the top. That'll be the numbers from 18 to 26. And I'll let you verify that those numbers in base 3 are indeed the numbers from 18 to 26. Okay, now let's see if this actually works. Suppose we take a number off the list. So let's take the number, let's just pick one, 22. 22, that is here. Where else do we have a 22? 22 is here. And the 22 is also here. Now 22, there is a 1 in the 1's place in base 3. For 22, there is a 1 in the 3's place, base 3. And for 22, there's a 2 in the 2's place. So written in base 3, this is equal to 211 base 3. So I need to take 18 off this card. I need to take 3 off this card. I need to take 1 off this card, which makes the pattern work. So anyway, that's the logic as to why this card actually works. This trick actually works using base 3 arithmetic.